Assalamualaikum to Dr. Aslina. We are from Group 2 are going to present about the question 2, which is the model and simulation of the sudden contraction duct. First of all, my name is NURAINA NABILA RUZI, metric number 199141, and my group mate is Steven, metric number 195666. So next I will talk about the objective of this question 2, which is to simulate the computational fluid dynamics using ANSYS Fluent software, and also to study the specific flow problem for turbulent flow in steady states and incompressible flow. So next I'm going to explain how we are going to simulate this simulation. We are using ANSYS Fluent. So first is to generate the geometry. The sudden contraction duct has been drawn using design modeler that has been provided in the ANSYS software. The next is to generate mesh. Okay, this method is to influence the accuracy, convergence, and speed of the solution. All the boundary condition is determined, which is there is the inlet, outlet, and also the boundary wall. And next is setup. The K epsilon model has been used, and the fluid has been set as a water, which is to be run in the model. And then the mass flow rate is entering the inlet of the duct, which is we are set it to 50 kg per second and also 300 kg per second. As a solution, there is several type of flow has been run with different flow rates. In this simulation, we just focus on steady state, turbulent flow, and incompressible flow with different inlet mass flow rate, which is 50 kg per second and also 300 kg per second. As a result, the contour plot, streamline, vector, and graph of the velocity and pressure has been produced at the end of the simulation with the different mass flow rate. So next about the boundary condition. So this is the inlet and the outlet, and the blue line and the yellow line is the boundary wall. Okay, next I will explain about the summary of boundary condition that have been used to simulate in the ANSYS, and this summary is applied to has been applied to other simulation also. So the mass flow rate has been used is 50 kg per second and also 300 kg per second. As it is in the steady state of the turbulent flow, the turbulent intensity have been set to 4.51%. And also this simulation this simulation is assumed to be in incompressible flow. So the temperature was in constant, which were 288.16 and I think 298 Kelvin, and it's assumed no adiabatic flow. There is a pressure, density, and also the viscosity, and there is also no slip condition, and the standard wall roughness has been considered. The roughness constant was set to 0.5, which indicates a uniform wall roughness. Okay, the next is the result. For the steady state of turbulent flow, the velocity, magnitude, and the dynamic pressure through the sudden contraction that was increased at the outlet. It can be shown in the figures. For an example, at point position of 70 meter, which is at the outlet, the velocity magnitude at mass flow rate of 50 kg per second increased to 0.00675 meter per second. And the dynamic pressure was also increased to 0.0225 Pascal. Okay. The next is also for the 300 kg per second. The graph is the trend of the graph is shows the same, which is, for example, I mentioned for the 70 meter for the outlet. the velocity magnitude is increased to 0.04 meter per second, while for the dynamic pressure is increased to 0.8 Pascal. So that's all from me. Next, I will pass to Stephen. Thank you.
Good morning, Doctor. I am Stephen. Now I'm going to present the contour and the vector shape of our static contraction uh, that has been produced by the simulated through uh, ANSYS. So first of all, we can see here, Doctor, that the velocity, the pressure contour is that has 50 kilogram per second. In the case number two, I mean the second one. The second one is the contour shape of the velocity. So firstly, Doctor, the evolution or the stream discharge of this velocity in contour has evolved in a way that point A to point B has increased its has increased its velocity, Doctor. Yeah, same also in the dynamic pressure, which also from point A to point B, it increases from the first shape. It was in around 1.2 negative. It was from 0.001 until it reaches to 2.4 meter per the 2.4 Pascal. Yeah. So from the second shape, Doctor, we can see that the velocity has changed significantly from its from the value of 1.5, around 1.5 to to 1 point uh, to 1.7, Doctor. So from this rate of change, Doctor, the value of a velocity has increased. As the same also, Doctor, in this case number two, which is 300 kilogram per second, the contour shape of dynamic pressure and the velocity has also evolved from point A to point B, Doctor. So in the same manner, Doctor, when the shape of the when the size of the shape has changed, the pressure also changes, Doctor. Uh, this is also theoretically agreed, Doctor, since the size of the size of the shape can affect the the uh, the the pressure or the velocity uh, from point A to point B, Doctor. So we can see, Doctor, here the vector of the velocity, the rate of change in 50 kilogram per second, Doctor, for the first case is it also shows that from 1.763 it changes when the shape changes to uh, to a sudden contraction also. So it increases from 1.763 to 7.53 meter per second, Doctor. The same goes to streamline, Doctor, the velocity. Uh, with the same case of 50 kilogram per second, um, they have uh, the same the same result, Doctor, which also increases from 1.763 to 7.53, Doctor. As you can see, though, there are streamlines. There are a lot of streamlines uh, that has been shown from the diagram. That's the same as well as the velocity. So the conclusion, Doctor, the flow problem of steady, turbulent, and incompressible flow had been determined by using computational fluid dynamics using ANSYS Fluent software. The simulation had performed using the differences of mass flow rate, which at 50 kg per second, 300 kg per second. The result of contour shapes, streamlines, vector, and graphs were determined for the turbulent flow at differences mass flow rate, which are the increasing of pressure and velocity through solid contraction duct. So these are our reference, doctor. And thank you so much, doctor. That's all for me.